short introduction. Next speaker is Tim Cruz, who has a long relationship with the Land Institute, on-site, off-site, but for the last 2-3 years, he has been the research director for the Land Institute. Distinguished ecologist, did pioneering work on the nitrogen cycle, and last sort of period has been focusing completely on making this transition to a perennial agricultural system. That's his main vision. So, welcome.
If anyone else wants to stand up and sit down and just move around for a minute, I'm happy to give that minute up. Okay. Well, it's a pleasure to be here. I always wanted to be a Pufendorf Fellow, and I've achieved it. So it's very exciting. Lennart, I really appreciate the opportunity to be here and to address everyone here. The title of my talk changed a little bit since the version that Lennart had that was put up here a little bit earlier, but it's basically the same theme. Harriet just gave a wonderful presentation of this arc of human food systems history, and I'm going to give another layer on top of that arc that describes some of the relationships our species has had with the planet about obtaining our food, particularly as it relates to energy. Now, I don't want to scare anyone. There's not going to be grand tables of numbers of kilocalories. There will be mention of calories and kilocalories. But I think that this is an extremely valuable way to really understand where we've come and where I think we'll need to go, and how this agricultural revolution that we're talking about in this conference could play a role. Energy does not come up very frequently in discussions of sustainable agriculture, but it is central to why we started doing agriculture in the first place. It is very much the primary human strategy to obtain calories. Look at this solar collector making us food. It's beautiful. There are many ecological challenges, however, with recreating this field of grain every year. I want to focus on the topic of energy in agriculture today because I believe it's going to become the focus of conversations a lot more as we try to back out of society's extreme fossil fuel dependency. There's good reason to expect renewables to come to the rescue to some extent. But it is hard to imagine our bodies not playing a more substantial role in food production at some point in the future. And I don't know, for those that were on the field trip to Hergestad the other day, if you noticed these statistics, but it turns out that the US is not the only country that's going down the path of fossil fuel dependency. And in fact, it has been an economic imperative to stay in the grain business, to replace humans with fossil fuels. So up until what I will refer to as, let's see, is that the right slide? Yes. That is not the right quote, though. I'm reading a few notes here to get ramped up, but this slide is here because essentially every animal, every organism has to capture more energy in the food that it eats than it spends in going after the food. It's a simple law, okay? And we are no different. This idea of calories, of food obtained relative to calories expended going after the food is often referred to as energy return on investment. And it's important to remember with this ratio, which is used a lot in the oil or energy extraction industry, that both the numerator and the denominator, if either of them go up or down, it alters the ratio, just like any ratio. You can think of this ratio in terms of a bag of grain. If a farmer consumes one bag of grain to farm a plot that then produces 10 bags of grain, the EROI is essentially equal to 10, okay? And how this ratio varied or stayed the same through time can help explain a lot of things about how our society developed the way it did, including, I believe, the original choice to domesticate annual grains rather than perennials. According to the Perennial Agriculture Project Global Inventory of Potential Candidates undertaken by Allison Miller's group at St. Louis University and the Missouri Botanical Gardens, there are 7,821 perennial grasses in the world, which is over half of the 11,313 species total in the Poaceae. And yet not a single one of these perennial grasses was domesticated to the point of becoming a major grain crop for our species. Why is that? Well, 9 years ago, my colleagues at the Land Institute published an in-depth paper in the Journal of Evolutionary Applications that explores hypotheses as to why annuals may have been favored over perennials in early grain domestication efforts. They listed a number of categories of hypotheses: physiological trade-offs, genetic mechanisms may have played a role, proto-farmer experiences in terms of the farmers dealing with low seedling vigor or less competitive in establishment. Imagine that. But a significant energetic consideration that did not appear in the paper, at least I could not find it, was a limitation on the process of selection itself, and that is the need to eliminate, that is, kill previous populations of a crop under selection, both to prevent cross-pollination with inferior plants somewhere nearby, but also simply to clear space to plant the next population. So let me unpack that a little further. The transition from hunting and gathering to incipient agriculturalists involves several types of inadvertent selection for specific crop traits. One that was super important, and we heard about it this morning, those of us that were there, was non-shattering seed. The selection for this trait, and that is the ability or the selection for plants that do not drop their seeds at the end of the growing season. The selection for this trait greatly increased the energy return on investment, or we'll call it EROI for short, of agriculture, and almost certainly played a role in why we adopted the annual ecosystem. Most plants in the wild have brilliant mechanisms for distributing their seed across the landscape. Again, this is referred to plant breeders as shattering. So most plants want to shatter, right? But we want crops that hang on to their seeds so we obtain the greatest possible yields for all of our hard work. This is maximizing EROI. So non-shattering tends to occur rarely, and it is a mutation in wild plant populations. But in fields where hunter and gatherers were collecting the first seed they would re-sow, there were some rare plants with this mutation of non-shattering with or that is a recessive trait that made the plants hold onto their seed. But those were definitely harvested, and the non-shattering gene became well represented in the seed of early grain crops. So by definition, the plants that they were harvesting were non-shattering, right? The rare plants. You re-sow those, the frequency of that gene increases in the population. You re-sow it again, it increases more, and eventually you have a domesticated or non-shattering crop. Some have suggested that wheats and barley could have made substantial shifts to non-shattering in as few as 60 generations. Something that was necessary for every round of selection is for the previous crop to have died. And this was not a problem with annuals, right? In order to re-sow the next generation and have a round cycle after cycle of selection. But it turns out that killing perennials is quite difficult. We're actually trying to do it at the Land Institute, figure out how to kill perennials without massive uses of herbicide or extremely deep tillage to undertake succession of perennial grain crops. And what we know is to try and knock off large fields of something like the Kernza perennial grain that we're seeing up here next to an annual wheat requires a tremendous amount of energy, and imagine doing it without metal tools. And because a simple act of growing and regrowing cycle after cycle of annuals resulted in substantial improvement of a number of traits, such as non-shattering, that carried positive energetic consequences, yield went up with little additional work required, resulting in EROI going up. Okay, so folks are with me? I mean, one simple example, though, of how annuals were a much easier route to get to this EROI than had perennials. And not to mention, why would we kill perennials? Why would the proto-farmers kill perennials in the first place? They observe that they regrow every year. Why kill them? You don't know that you're doing incipient selection for non-shattering, right? You would not spend that very, very precious energy killing plants, and yet you would need to clear large fields and have many, many, many selection cycles to achieve this increase in non-shattering and therefore energy capture in agriculture. But now I want to focus on EROI hitting a cap, which it did ultimately across all annual grain cropping systems. This is one of these path dependency things. It keeps coming up. Let's focus on this range of EROIs for a second, 10 to 40. A high EROI value means that there's a lot of grain produced per work effort, which translates into there being food to do other things than farm. Things such as having kids, or playing music, or taking care of elderly people, or building temples, or fighting wars, or just about anything other than doing agriculture itself. Essentially, the high EROI subsidizes non-agricultural activities in life. And while there's a fourfold range in EROI, there's a cap on how high EROI can go. Even a ratio of 40 to 1, which is among the highest seen in non-fossil fuel agricultures, and it's a paddy rice system, necessarily equates to a majority of society working as farmers. That is because working hard as farmers, and that is because farming is hard work. That sentence explains the cap. In working hard, we expend energy, which is the denominator of EROI. Why does farming require so much work? It's funny to even ask this question. We so associate farming with hard work that it's just like a given, right? One reason, and maybe the most important, is that farmers are constantly battling ecological succession. The supermajority of terrestrial ecosystems are dominated by mixtures of perennial plant species. The vast majority. Intense natural disturbances can pretty much demolish these ecosystems from time to time. And this is when annuals, one of the critical roles annuals play ecologically, moving into disturbed areas, germinating quickly, and growing fast. And I might add that the perennial cover that takes the place of annuals, which eventually outcompetes the annuals and comes to dominate, again, virtually the vast majority of terrestrial ecosystems. These perennial systems sponsor higher productivity, net primary productivity, than the annual ecosystems. So when we insert annual agriculture into an ecosystem like this, we should realize that we are trying to block a force of nature called succession. And that requires a huge amount of work. Arguably the number one human activity in the last 10,000 years, what people have spent more time doing than any single other activity, is battling succession through clearing vegetation and weeding. We're weeders, pretty much, yeah? In waging this war on succession, not only do we prevent perennial vegetation from establishing, we prevent the ecosystem services that the perennial vegetation provides from taking place. Ecosystem services like soil formation gives way to soil erosion. Building soil organic matter gives way to loss of soil organic matter. Having ecosystems resistant to pathogens and insects primarily because of diversity makes them vulnerable to pathogens and insects. Ecosystems that retain nutrients remarkably to ecosystems that leak unintentional nutrients, have unintentional nutrient losses. Ecosystems that use water and precipitation efficiently to ones that have low precipitation use efficiency. And we're learning ecosystems that may have high functioning microbiomes give way to ecosystems that have relatively low functioning soil microbiomes. The combination of arresting succession and compensating for poor ecosystem function helps explain why EROI was capped in pre-fossil fuel societies. A major implication of annual agriculture having a cap on productivity is that most people in agricultural societies farmed. And according to Paul Gordon at the University of Montana, in the year 1800, arguably the dawn of the fossil fuel era, 3/4 of people were working in some form of slavery, serfdom, or other indentured servitude on the planet. And the majority of them labored in agriculture. I didn't do that research, and I don't know how close it is to the truth, but it is a fairly large percentage of humanity that was doing agriculture because they had to, and not just for food, but for other people. But then the fossil fuel bonanza arrived and gradually released many, but not all, of the world's people from very arduous agricultural work. And it's not a coincidence that at the end of slavery in the US coincided with this historic event of the first oil well being drilled in Titusville, Pennsylvania in August of 1859. Our big brains, already very calibrated to thinking about energy, quickly figured out ways to spend our newly unleashed reserves in ways we never could have imagined before, such as moving a several-ton vehicle 5 kilometers to acquire a quart of or a liter of milk. Who would have imagined? And we quickly realized that we could put this energy to use in raising yields. To hell with EROI. Doesn't matter anymore. We have all the energy we need, and it's free. They're fossil fuel slaves. They don't complain. Let's put them to work. In some crops, we could even flip the balance of the EROI ratio and spend more calories on producing certain foods than they provided. We put more fossil fuel energy in and get less calories out. It's remarkable. We have successfully applied fossil fuels to relax or eliminate every ecological limiting factor virtually in agriculture. Comparing pre-fossil fuel with industrial fossil fuel maize production, these are data from Pimentel and Pimentel. I didn't have that on here, 2008. We have the caloric input per hectare goes up some 16-fold in the transition from traditional to industrial agriculture. The percentage of input energy derived from fossil fuels goes up from 0 to almost 100. The caloric output only goes up about 4-fold. Okay, so the input of energy goes up 16, the output goes up about 4. Thus, the EROI drops from 10.7 to 1, at the 1 being a solar calorie that came through photosynthesis and was eaten by the farmer, to 2.5 to 1, with the 1 being a fossil fuel calorie in that system. Industrial agriculture essentially added insult to injury when it came to farming a compromised ecosystem. We have been able to push continuous cropping onto lands, onto lands that could not have supported it before fossil fuels. But some of the similar some of the insults span both traditional agriculture and industrial agriculture. But the scale has gotten more dramatic and the inputs have gotten more dramatic. Take nitrogen fertilizer, for example. It's come up in this meeting a handful of times. With incredible supplies of energy, we can actually accept the practice of losing 50% of the nitrogen applied to a grain field as business as usual. Nitrogen being the most energy expensive input into industrial agriculture. And there are off-site environmental consequences to poorly functioning on-farm ecosystems. Take the dead zones that have established in many marine ecosystems around the world, driven by nutrient runoff primarily from agriculture. And this time series of maps shows the increase in the hypoxic zone in the Baltic Sea from 1906 to 2012. Increasing in size from around 5,000 square kilometers to 60,000 square kilometers over the past 115 years. I believe it is the largest dead zone in the world, but I'm not sure. There might be someone in here that could confirm that. So if we could just eat the fossil fuels directly, we would save a lot of agricultural lands from degradation. But I think there's a better longer-term solution than even that. What if we move agriculture down this successional gradient? The gradient that ecosystem is trying to go in the first place, and not arrest it with annual intense disturbance and holding it there to let these seeds every year have a chance, but rather move it further along, and in doing so, capture the ecosystem benefits of soil protection, carbon and nutrient retention, weed suppression, and functional soil microbiome that exist further down this successional gradient. And we know that from studying natural systems in that stretch of succession. These data from Steve Coleman and colleagues at Kellogg Biological Station underscore the advantage of adding a perennial to the ecosystem versus annual wheat. On the y-axis is kilograms of nitrate N lost per year from 3 different rates of fertilizer application there on the y-axis. On the left is year 1, and on the right, the establishment year, and on the right is year 2, once the perennial crop, which is Kernza, the wheat relative that the Land Institute is developing. We'll be hearing about that shortly. Juxtaposed against annual wheat. And this is how much nitrate is escaping below the root zone of these crops. And we can see that in the establishment year, the perennial system is pretty leaky. Those root systems aren't very well developed, and they're leaking about as much as the annual system in this case. But in the perennial system, once established, or excuse me, after the establishment year, the perennial has almost non-detectable levels of nitrate leaving the root zone. And we heard a very similar story from Alex Hubble, who was at sites over near Alnarp, the site's long-term experiment plots. Alex is doing a similar comparison and reported that preliminary results are that the Kernza is leaking about 100th of the nitrate below the root zone as the annual wheat is in that system. And if we diversify the agriculture by, for example, adding the very important functional group of a legume that can fix nitrogen, as Wes described yesterday, with enzymes at ambient temperatures and pressures versus the Haber-Bosch process, which, again, uses prodigious amounts of fossil fuels. Jerry Glover put this energy comparison together of how much fossil fuel underlies the inputs to grow wheat in Kansas compared to growing a perennial grassland in Kansas on an annual basis. Not that the perennial polyculture will necessarily get away with this low of an energy budget that we're seeing on a prairie hay meadow, but it's going to be closer. And this slide certainly underscores the role that nitrogen plays in the energy economy of modern agricultural systems. So back to this figure, I'm going to wind up with this. This figure, again, it has two moving parts, the energy return on investment on the y-axis and the yield on the x-axis. And in early agriculture, as we were selecting things for like non-shattering, we went up. We both gained yield as we gained EROI, right? And then with the fossil fuel bonanza, we broke through, energy didn't matter, and we went way up on yield, but at a serious cost of energy return on investment. And now, for arguably the first time, and at a very important time, there's the prospect of continuing on the line of improving yield and energy return on investment if we're not battling the ecosystem and as a result, creating an ecosystem that is very compromised in its function. And breaking through the cap will have profound implications whether you live in a highly industrialized or a subsistence economy. The model of grain agriculture that feeds us today is based on deep intervention in and disruption of ecosystem processes. This requires a great deal of energy, human and fossil, to maintain. And the resulting ecosystem does not function well. By incorporating key elements of what makes natural ecosystems sustainable, such as perenniality and diversity, we expect that the work required to farm, human and fossil, to diminish, with EROI rising accordingly. And this is one part of a hopeful path forward into a post-fossil carbon future. And I thank you for your attention, and I'd love to take a couple questions. Thank you. Preguntas. Valentin.
In your graph of increasing yield and the EROI, do you think we need to get to that higher yields, or we could, with perennial grain polycultures, could we accept lower yields and be efficient, assuming a transformation of the whole energy efficiency?
Sure. The phrase "going where no grains have gone before" implies a level of ignorance about where that's ending up. And without question, I think we could do quite well not matching the yields of current grain elite annual crops. But I also don't dismiss the possibility of exceeding those yields. I don't see a theoretical reason to suggest that that's not possible. So I don't even really want to limit us. I'm sure with some crops we wouldn't get there. With others we might go beyond. But I guess the main point is we probably need to have higher yields than the land races produce right now, which is the top of this EROI curve. And I think we can do it while not having the energy footprint that was required in an annual ecosystem. Yeah.
First of all, congratulations for the splendid lecture. Maybe a naive question, but when we think about the perennialization, are we thinking mostly of our grain crop, or are you guys even thinking of our horticulture that for me, it's very hard to imagine becoming perennial?
It's a great question. I mean, we definitely support people. We encounter people interested in working on vegetable crops, some of which are already perennial, such as tomato, and there's chilies that are perennial. There's many species that would lend themselves to perennial work, and there's others that are kind of nonsensical, that we eat the whole plant, and probably and potatoes and stuff like this, which is an unusual case. But we've focused on grain crops, especially because of the role they play in providing caloric value to our species. 70% of the calories we eat, either directly or indirectly, come from these grains. But there's no reason why we shouldn't be working on other crops as well. And in fact, some of the worst EROI examples that I was referring to are like tomatoes. So not very many grain crops go below the zero, the Mendoza zone there of perennial grains. Yeah.
The microphone is up there. So.
Okay.
I will ask first. So if we put your theory in the context of climate change and fossil fuel-free energy transition, how do you go further? Because as I understand, in your thinking, you still kind of think of farming with perennials, but with fossil fuel-free inputs. Or what is the next step?
Well, it was subtle, and I was kind of reading away here, but I did make the comment towards the end there that these ideas of improving EROI and yield are very profound in my mind, both in an industrialized and a subsistence economy. Our germplasm is being trialed in sub-Saharan Africa and would be extremely, I think, useful in subsistence systems, both to build soil organic matter, which is very difficult to build with almost no inputs, but also to reduce the amount of labor required for that agriculture. We don't think necessarily of our agriculture being in one camp or the other, and ultimately, I began the talk by suggesting I think we will have more human labor in agriculture in the future, almost without question. That's my own personal perspective. It would be extremely valuable in either context, I guess is what I'm saying. And Oh, sorry, Peter.
Well, thanks for a very exciting presentation. Perspectives. If I were a farmer, I really would rush away for the perennials, because then I will only need one machine, the combine. And
they do need to get
selling
planted now and then, but
don't
there
even
could
need
be
a
a
tractor.
cooperative, yeah.
But anyhow, that will you substantially reduce the amount of labor you put into the grain production, and we'll get rid of even more opportunities to work on. And I don't regret that, because it's a hard work. Well, anyhow.
I think we might reduce the inputs more than we reduce the labor, but
well, if I don't plow and I don't harrow, I don't sow, then I mean I don't need all those machinery and I don't know this workforce.
Yeah.
I just the sow machine once every 5 years or 3 years maybe.
Okay, yeah. So it would vary on the crop.
Which means that the perennials are not really perennials forever. They are semi-perennials. I mean, you have to resow them every 3 years or something, every 5 years.
It will vary a lot based on the crop.
Yeah, but
some may go to 10 or 20.
Well,
yeah.
But
the rice hasn't slowed down yet. It's at 4.
But the exciting thing is that all the benefits that you are, and I really hope you will come through with them, because it's such an enormously advantage compared to the system we have today. Mm-hmm. But it has taken a couple of thousand years to reach the yield that we have on the annuals today. And you will take about 10 or 15 or maybe 20 years before the perennials you domesticate now will reach the same level or closer to the level. So what do we do in between? Because we have a dramatic need for change in agriculture, or agricultural revolution.
I guess a couple of responses to that. There is a 50-year farm bill that the Land Institute has out in the world that discusses how we might go from where we are today to 50 years out, where there's a lot more perennial germplasm to plant in the landscape. And what we have today that we could implement in terms of cover crops and perennial pastures and smaller areas of perennial grains that might make sense to start that transition. And it's a really interesting document just in terms of a thought experiment of what the best practices might look like to get us to a much broader implementation of perennial agriculture in, say, 50 years. But it's also important to recognize that there are perennial grains. When we talk about Kernza, and this will be discussed more shortly, but it is a domestication species starting from a wild plant. There are examples of wide hybrid crosses, with perennial rice being the most exciting. I'm not going to even steal the thunder, but it has really high yields. And there's also some other crops, such as sorghum, wheat, that present genetic challenges, but that we believe, and there's evidence to suggest that they can be worked through in certain instances anyway, and we may get to some more viable perennial crops sooner than later if those work out. So that is another avenue that has some promise in terms of the nearer term. Yes.
Yeah. About food waste, I study supply chain management, so and I'm doing my thesis on food waste now. And I was just curious if you consider excess yield and the energy that goes to destroying it in this graph, and can you apply it to enforce some laws to have maximum yields to countries or something to address food waste?
Yeah. There's no question in my mind that the cheap food that the fossil fuel-based food system produces and the economy that drives us to produce cheaper and cheaper foods has contributed to the food waste problem. If I don't think we see that level of food waste in certain parts of the world where we're working really hard for that food, even if the agriculture is as productive. I guess I would be surprised if in that blue line world if productivity is the problem, I don't think the food will be as cheap as it is when we have one person in a combine farming, 3,000 hectares. It's going to be a different economy. It's a longer conversation, but anyway, it's an interesting question as to whether the productivity per se is the problem here, or if it's another aspect of the food system. Generally speaking, the polycultures that we're talking about are not likely to have the same yield of, say, one of the grains per hectare as a single species stand. And thus, we are likely to have a reduction in yield per area, even if it's yielding really high, if we're sharing that landscape with a legume, for example. So there's many moving parts. It's an excellent question, though, and it might just be a little complicated for the minute we have left.
We have one short question and short answer between us and the coffee. And I think Eric has the microphone.
Maybe it's not short, but I'll try. Thanks a lot, Tim, for inspiring talk. What you said and talked about in this EROI thing, and also your comments about the labor in food production, it made me think that we are also facing that maybe many people around the world need to reconnect with how their food is produced. We have great problems with obesity, cardiovascular diseases, diabetes, and still the number of fitness centers are growing. So maybe we need a curve for human spent energy in the EROI also, in order for us to contribute actually more and use this opportunity for many purposes, like each of us may also have a responsibility in combating climate change.
I couldn't agree more. The photos that were of the women working weeding on a couple of slides were from my daughter, who worked in the Peace Corps in Burkina Faso. I went to visit her and saw the most fit people I've ever seen in my life. Never anything coming out of a gym quite like the people doing that work. And I was like, that's what humans look like. But there's no, and I guess the issue is 10 to 40 is probably more work than even they want to do. And therefore, 80 or 100 is still a lot of work, but it would be more doable. There would be a lot more excess food for other things in society. Add some renewables, probably some fossil fuels at the end, and I think we have a livable world. But thank you. That's a great comment. So thank you all.